All right, welcome to your favorite class. My name is Ron Patton. This is Calc 2. I hope you're doing well. I hope you're doing well. All right, so I am beyond excited about today's because we're talking about the Maclaurin series. This is, I love Taylor, but I love Maclaurin even better. All right, so the reason why is that Maclaurin series um, is very similar to what we've already seen before. Okay. And this represents a function of an infinite sum, but this is a super special function. Okay. And the reason why is this is super special is because it um, it has the value that you're centering it at is always going to be zero. So it's a special case of a Taylor, and it's so special I gave it its own name. So the Maclaurin series. All right. So if you ever see centered at zero, Taylor series where it's centered at zero, or you see a Maclaurin series, you just know it's centered at x is equal to zero. I did notice right before I started this that I do have a typo. So this right here should be a zero because n is going from zero to infinity. So you're actually doing this the function as is at zero, and then you're taking the first derivative of I by wherever you're at, like which term you're at, the factorial, appropriate factorial. All right. So, but the key is that this is centered at zero. All right. So let's go on, and I will have the slides fixed with that small error. But let's go on and do an example. All right. So, for example, let's say we have this ugly function f of x is equal to x e to the 2x. And we're just trying to figure out, what is this Maclaurin polynomial? So, and we want it to the third degree. So I would take f of x is equal to x e to the 2x. And then I got to take a derivative. So this is a product rule. So if I do that, I would have e to the 2x plus 2x e to the 2x. All right, so then what about if I take second derivative? So you got to pay attention. So I've got 2e to the 2x plus, I'm going to take a derivative with respect to x here. So I've got 2e to the 2x. And then I'm taking derivative of e to the 2x. So I'm going to end up with 4x e to the 2x. Now, if I add up everything all like terms, I should end up with 4 e to the 2x plus 4x e to the 2x. So what about the third derivative? And the third derivative is as far as I need to go because I just need to go to the third degree. So I would have 8 e to the 2x plus, I'm going to take derivative with respect to x, so I'd have 4 e to 2x plus, now I'd take e to 2x power. So I'd end up with 8x e to the 2x. And if I combine like terms, I should end up with 12 e to the 2x plus 8x e to the 2x. All right, so now the wonderful thing is that we want it where x is equal to 0, where we're centering it at 0. So if I take 0 and plug it in to each of these derivatives, I will get the following. So if I plug in 0 to this first one, I get 0. If I plug 0 into my second one, I really just get 1 because this 2x e to 2x is going to go to 0. So what about the third one? The third or the second derivative, I should get 4, and in that third one, I should get 12. So what is going to be my polynomial? So my third degree polynomial is going to be 0 plus 1 over 1 factorial x plus 4 2 factorial x squared plus 12 over 3 factorial x to the third power. So I should end up with x plus 2x squared, because 4 divided by 2. And then 12 divided by 6 is going to give me 2x to the third power. So this is going to be my third degree Maclaurin polynomial. And it's actually pretty nice and pretty slick. All right, so let's go to example 2. So example 2 gives you a lot of information. So it actually gives me my function, which, oh, by the way, I have no clue what it is, but it tells me what the appropriate values are for the derivatives whenever I plug it in. So it says, what is Maclaurin polynomial for degree 3? Well, all I need to know is that I'm just going to have this g0 plus g prime of 0 divided by 1 factorial x plus second derivative at 0, 2 factorial x squared plus g the third prime or third derivative of 0 divided by 3 factorial x cubed. So g0 is 3. I get the first derivative is going to be a negative 2 over 1x plus the second derivative is a 1 over 2 x squared plus the last one is a negative 3 over 3 factorial. So 3 factorial is the same as 6. I'll write down as 6x to the third. So if we clean it up a little bit, we should have 3 minus 2x plus 1 half x squared minus 1 half x cubed. So that's my third degree polynomial. For this, honestly, it's an unknown function, but I do know what's happening at the derivatives at 0. All right, so now I want you to try this. Please put this on pause, see if you can get it. Um, Thank you very much for taking off pause. The correct answer is 27. And the reason for that is because we need a coefficient, okay, the coefficient of x to the fourth. So let's walk through that real quick. So if I need the 4x to the fourth, so that's going to be the fourth derivative. So let's say I've got f of x is equal to cosine of 3x. Then the first derivative is going to be a negative sine, negative 3 sine of 3x. The second derivative is going to be negative 9 cosine of 3x. The third derivative is going to be a 27, positive 27 sine of 3x. And then that fourth derivative is going to be a positive 81 cosine of 3x. Now, we're looking at the coefficient here, so remember that this is going to be the fourth derivative at 0 over 4 factorial x to the fourth. So we're not interested in it, we're actually interested in this. So if I plug 0 in, I should get 81 over 4 times 3 times 2 times 1. 3 goes into 81 27 times. So I should get 27 over 4 times 2 is 8. And that's why I get the answer of 27 over 8. Anyway, so I hope this helps. This makes sense. These are different ways that you can play around with Maclaurin polynomial as well as Taylor. And at this point, hopefully you should be good to go. Okay, finding parts or point estimates or any of that stuff with this Taylor and polynomial. I mean, it's actually fun. It's fun just to see how this works out, and you can take a very complicated function and get a very easy to use polynomial from it. All right, you should be good to go. Giddy up, and look forward to seeing you.